Welcome back to the next video, everybody. Today we're going to get another perspective on deformation problems. So let's take a look at that. Let pi be a profinite group satisfying the p-finiteness condition from the first video of this chapter. Let's let k be a finite field with characteristic p. Let's let v bar be a finite dimensional k representation space for pi, and we'll assume the associated representation is continuous. If B is a coefficient ring with residue field k, a deformation V of V bar to B is a pair V alpha, where V is a free B module of finite rank with a continuous pi action, and alpha is an isomorphism from V bar to V tensor K over B as pi representation spaces, okay? Now the functor dV bar of B will mean the set of isomorphism classes of deformations of V bar to B. We should view D sub V bar as a covariant functor from the category of coefficient rings with residue field K to the category of sets. Once we fix a K basis of V bar, we can identify the K automorphisms of V bar with GLN of little k, where n is the K dimension of V bar. And the pi action on V bar then just gives us a continuous residual representation rho bar from pi to GLN of K. And then so directly from the definitions, we have an isomorphism of functors D sub V bar to D sub rho bar. Okay, so basically this perspective that we're taking, this kind of module theoretic perspective on the representation space, is up to isomorphism the same thing as the perspective on coefficient ring lifts that we took over the previous videos. Okay, we can also phrase things another way in the relative setup. So instead of looking over the residue field K, we'll look over a coefficient ring A with residue field K. Okay. Under that setup, let V bar be a free A module with rank n with an A linear continuous pi action. And if rho from pi to GLN of A is the continuous homomorphism obtained from V bar by choosing an A basis, then if we denote by D sub V bar the functor, which takes an A augmented coefficient ring B with residue field K, spits out the set of isomorphism classes of pairs V alpha, where V is a free B module of rank n endowed with a B linear continuous pi action, and alpha is an isomorphism from V bar to V tensor A over B of A double bracket T modules. Then there's a natural isomorphism of functors from D sub rho to D sub V bar. This is the relative deformation problem rephrased, okay? So when I say relative, I mean we're working relative to a coefficient ring, not relative to the very base residue field K. Okay, so that's the non-relative setup or the absolute setup. Okay, so we can return back to the absolute deformation problem. So that's when we're working kind of over K instead of over a residue field with coefficient ring K. And we can say a little bit more. We'll let V bar be a finite dimensional K representation space for pi with the action continuous, such that the natural map from K to the K bracket pi endomorphisms of V bar is an isomorphism. So for example, by Schur's lemma, this will happen if rho bar is absolutely irreducible, as we've seen already actually in previous videos. However, there are definitely examples of rho bar which are not absolutely irreducible that will still satisfy the property that this map is an isomorphism. Okay, so for example, let's let rho bar from pi to GL2 of K be a representation equivalent to the form rho bar of G is chi of G, U of G, 0, eta of G, which is not semi-simple. In this case, this is equivalent to the condition that the image of rho bar has order divisible by P, which is the characteristic of K, and such that one of the two characters, chi or eta on the diagonal, is non-trivial. This isn't a contrived example. Representations like this occur among the residual representations attached to elliptic curves with ordinary reduction over p-adic number fields, for example. Okay, so then it turns out the pi representation space V bar attached to rho bar is not absolutely irreducible, but it does satisfy the condition above that this map up here is an isomorphism. Okay, so that can be checked. Let's rephrase the representability proposition of the previous video in this case under this new perspective. So proposition 5 with all of the above notation and under the above setup, D sub V bar is representable. That is, there's a coefficient ring R with a residue field K and a finite free R module V sub R endowed with a continuous pi action, which is a deformation of V bar to R, which is universal in the following sense. Any deformation via V bar to any coefficient ring A with residue field K comes from V sub R by tensor product via a unique homomorphism R to A that induces the identity on residue fields, so a coefficient ring homomorphism in other words, such that V is isomorphic to V sub R tensor A over R, okay? Now, let's let A be a coefficient ring with residue field K. If pi is a profinite group, V bar is a finite dimensional K vector space equipped with a continuous pi action, and pi and V bar satisfy the conditions of the previous section, we wish to study deformations of V bar to coefficient rings A, which are lambda algebras. Okay, so like instead of just considering deformations of V bar to just coefficient rings, we only want to look at the coefficient rings that are lambda algebras if lambda is a fixed coefficient ring also with residue field K. Of course, we also want the structure map from lambda to A to be a coefficient ring homomorphism. And there is such a structure map because that's what it means for A to be a lambda algebra. Okay, so let's let D sub V bar lambda denote the restriction of the functor D sub V bar to the category of such coefficient ring lambda algebras. Letting R denote the universal deformation ring of the pi representation V bar, whose existence the previous proposition guarantees, we have the following result, proposition 6. D sub V bar lambda is representable. By what? All you have to do is take R and tensor it up to lambda over W of K. Well, it's actually a restricted tensor product, where W of K is the ring of K Witt vectors, where this kind of restricted tensor, or this completed tensor product, is just the completion of the ordinary tensor product. Completion with respect to what ideal? The ideal M, which is the kernel of the map, from R tensor lambda over W of K, the ordinary tensor product, to K. The point is this. The reason you have to complete the tensor product is that it's not always true that the tensor product of two coefficient rings is still a coefficient ring, okay? And we want our category to be closed under tensor products. So we'll just take, well, we want our, under a suitable notion of tensor product, we're going to want our categories to be closed under tensor products. And the correct notion there is the completed tensor product. So for proof of this, you can see CSS page 265. It's really just all definitions though. Okay, so from here on out, we're going to fix the coefficient ring lambda with residue field K of characteristic P, and we'll use lambda as like a base ring. Everything will be kind of relative to that. More precisely, we're going to be working in the category whose objects are coefficient lambda algebras A, and whose morphisms are homomorphisms of coefficient lambda algebras. The default base ring for us will be lambda equals W of K, the ring of Witt vectors. Okay, so perfect. So we'll keep pushing on further into chapter 8 next video. I'll see you then, and thanks for watching.